Okay, so today we'll start a new module of our AICTE based lecture series, right? The fifth module, the periodic properties. And today's first lecture will cover the concepts of shielding, the concept of penetration of orbitals, the variation of energies of S, P, D and F orbitals due to the effect of shielding and penetration, and as a consequence we'll find how they affect the electronic configurations of various elements with the exceptions, and lastly we'll cover the Slater's rule for computing effective nuclear charges. Right. Okay, now let us first discuss the concept of shielding. For a multi-electron atom, right? Now we'll consider here multi-electron atom, not those like hydrogen which has only one electron. Any single electron in a multi-electron atom experiences both the positive charge of the nucleus, which is in fact attractive, and the negative charges of the other electron, which are repulsive. We can think of this repulsion of one electron by another electron as screening or shielding that electron from the full effect of the nuclear charge, right? For example, let us consider the lithium plus, right, or lithium ion. Because the lithium ion contains two electrons, its electronic configuration is identical to that of helium, that is 1s2, and these two electrons will occupy the 1s orbitals. Let us draw the picture with the nucleus with the 3 plus charge and the electron residing in them. Right? Now, though I have drawn a circle here, this is a sphere, and the electron, these two electrons can be anywhere in between them. Okay. Now you see, let us imagine that there is a third electron which is coming towards the lithium ion. When the third electron is far from the nucleus, it experiences the plus 3 charge of the nucleus through the screen or the shield of the 2 minus charge of the two 1s electrons, isn't it? That means it is screened, or it is feeling that there is a shield or screen of 2 minus charges in front of the nucleus, in between it and the nucleus of 3 plus charges, as is shown in the diagram. We can think of this third electron as an experiencing an effective nuclear charge of approximately plus 1, because 3 is from the nucleus and 2 minus from the electrons. As a whole, it is giving a net charge of plus 1. The inner electrons in effect is shielded, or sorry, the inner electron is actually effect shields the outer electron from the full nuclear charge. This is called shielding. Okay, now this time again let us draw the same picture of the lithium plus system with two electrons, right? Only thing is, now let us imagine that the third electron comes much closer to the nucleus. As the electron penetrates the electron cloud of the 1s electron, it begins to experience the 3 plus charge of the nucleus more fully, because the third electron is less shielded by the intervening electrons. If the electrons could somehow get more closer to the nucleus than the 1s electron, it would experience the full 3 plus charge, as it is seen here. In other words, the outer electrons undergo penetration into the region occupied by the inner electrons. It experiences a greater nuclear charge, right? And therefore becomes more stable. Why it is more stable? Because from the Coulomb's law, we know that the energy of the two charge interaction of two charge is inversely proportional to the separation between them, right? And if they are opposite, this value becomes negative. So as this value decreases, it is more negative, that means more stable. So this is important, that due to penetration, an electron in an orbital becomes more stable, right? Okay, now let us recall the radial distribution functions of an atomic orbital, right, which we discussed during our discussion of first module, the shapes of the orbitals and the graphs, all those things, right? This shows that the total probability of finding the electron within a thin spherical shell at a distance r from the nucleus. The figure on the left hand side is showing the radial distribution functions of 2s and 2p orbitals superimposed on one another. The radial distribution function of 1s is also shown in the green. If you notice that there is in general an electron in a p orbital has a greater probability of being found closer to the nucleus than an electron in the 2s orbital. We might initially expect, therefore, that the 2p orbital would be lower in energy. However, exactly the opposite is true. The 2s orbital is actually lower in energy, right? And we know this, and this is due to the bump near the nucleus for the 2s orbital. The bump represents a significant probability of finding the electron very close to the nucleus. Even more important is that this area of probability penetrates into the 1s orbital. That means it gets into the region where the shielding by the 1s electron is less effective. In contrast, most of the probability in the radial distribution function of 2p orbital lies outside the radial distribution function of 1s orbital. Consequently, all of the p orbital is shielded from the nuclear charge by the 1s orbital. The 2s orbital, as it experiences more of the nuclear charge due to its greater penetration, is lower in energy than the 2p orbital. This explains why the third electron in the case of lithium goes to the 2s orbital rather than in 2p, right? And this also explains that the sublevels under the principal quantum number, that is 2s, s and p, why they are differ in energy. This difference is due to the extent of penetration of the orbitals due to the spatial distribution, right? Similar situation is faced when you compare 3s, 3p and 3d orbitals as seen in the diagram on the right. The s orbital penetrate more fully than the p orbitals, which in turn penetrate more fully than the d orbitals, right? Okay, so by the discussions of shielding and penetration of orbitals, we arrive at the energy ordering of the various orbitals in multi-electron system as shown in the figure along the right hand side. Because of this penetration, we note that the sublevels of each principal level are not degenerate anymore for a multi-electron atom. And in the fourth and fifth principal level, this effect of penetration becomes so important that the 4s orbital is lower in energy than the 3d orbitals, and the 5s orbital is lower in energy than the 4d orbitals. And you also note that the energy of separation between one set of orbital and the next level becomes smaller for 4s and beyond. And the relative energy ordering of these orbitals can actually vary among the elements. and this is important, right? So these energy differences is not same among all the elements. They vary along the elements. They depend on the number of electrons present there. This variation results in irregularities in the electronic arrangement of transition metals and their ions. For our convenience, we can write down the energy ordering as 1s less than 2s, then 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, and so on. Now that we know the energy ordering of orbitals in a multi-electron atom, we can determine the ground state electronic configuration for rest of the elements. Because the electrons occupy the lowest energy orbitals available when the atom is in ground state, and only 2 electrons with of course opposite spins are allowed in each orbitals, we can systematically build up the electronic configuration for elements. This pattern of filling is known as Aufbau principle. Aufbau means in German the building up of the electrons in an atom. The order of energy of the orbitals strongly depend on the number of electrons present in the atom and may change on ionization also. For example, the effect of penetration are very pronounced for 4s electrons in potassium and calcium. In fact, this energy ordering is good only up to the Z, or the atomic number is less than 21, that is up to 20, that is calcium. Beyond that, from scandium, the energy of 4s and 3d are very close to each other, and in fact the 3d orbital is in the neutral atoms lie close but lower than the 4s orbital from scandium to zinc. In atoms from gallium, that is 31 onwards, the 3d orbitals lie well below the 4s orbital in energy, and the outermost electrons are unambiguously those of 4s and 4p subshells. Now, up to 18 atomic number, that is argon, there is no ambiguity. Okay. Next atomic number is 19, that is for potassium. So for potassium, it's after filling the 3s and 3p with 8 electrons, that is a closed shell of argon configuration, the next electron, the 19th electron, actually occupies the 4s orbital, which is next in line for occupation, right? So the configuration is effectively argon and then 4s1, right, leaving the 3d orbital vacant, because in this case the 3d is higher in energy for 4s. Similar is the case with calcium. The next electron enters the 4s electron, giving the configuration of argon and 4s2. This is the analog of magnesium. However, in the next element, scandium, the added electron occupies a d orbital, and filling of the d orbital begins from here, from scandium to zinc. We also note that in some cases, a lower energy may be obtained by forming a half-filled or a full-filled d subshell, even though that means moving an s electron into a d subshell. Therefore, a half-filled d shell is approached, right? The ground state configuration is likely to be d5s1 rather than d4s2, as in the case of chromium. Or as a full d subshell is approached, the configuration is likely to be d10s1 rather than d9s2, as for copper. Or in case of palladium, we see it's d10s0 rather than d8s2, right? like nickel. A similar effect occurs where f orbitals are being occupied and the d electron may be removed into a f subshell so as to achieve an f7 or a f14 configuration with the net lowering of energy, as in the case of lanthanides. This is a direct consequence of spin correlations, right? Then the 3 or d orbitals, the 4s orbitals are filled first. That is because for elements with incompletely filled d subshells, the determination of actual ground states is not just by these simple considerations, but also spectroscopy calculation is taken into account, right? And moreover, we see that this energy ordering, right, of are for individual atomic orbitals and do not fully take into account the repulsion between the electrons, right? That's why we get this type of ordering. But as we go on filling of electrons, there are electron repulsion also. That has to also be taken into account. Right. Now, these spectroscopic calculations sometimes show that it is advantageous to occupy orbitals predicted to be higher in energy than going to the 3D orbitals. The explanation for this order is that the occupation of orbitals of higher energy can result in a reduction in the repulsion between the electrons that would occur if the lower energy 3D orbitals are occupied. It is essential that when assessing the total energy of electrons, we consider all contributions of the energy of the configuration, not merely the one electron orbital energies, right? The energy ordering of the Aufbau principle that we are used to see is actually the one electron system, right? Now, spectroscopic data shows that the ground state configuration of these atoms are mostly of 3dN and 4s2 type, right? The 4s orbitals fully occupied despite individual 3d orbitals being lower in energy. Okay. The last topic for today's lecture is Slater's rule to determine the effective nuclear charge by calculating the shielding constant S. Now, first of all, we have to understand that these rules are semi-empirical and only give us approximate values. Now, let us go back to the rules. There are 4 rules. The first one is how to write the electronic configuration for this calculation, right? The electronic configuration should be written in groups as shown here, right? Despite of the energy ordering and all that, what we learned before, we should write the electronic configuration in groups like this. Okay. Each parenthesis signifies a group. The second rule states that electrons in any group higher in the sequence than the electrons under consideration will not contribute to the shielding constant, right? Now, to understand this, let us take specifically the example of, say, a 4s or 4p or say 3p electron, right? Now, if we consider a 3p electron, we will not consider the electrons which are on the right hand side of it. We will only consider the 3s and 3p electrons which are there and on the groups that are on the left side of it, right? And if we consider, suppose say 4d electron, similarly we will not consider those are on the right hand side, that is 4f and beyond it, right? We will only consider which are below. Now, coming to the third rule, right, which is for only s and p orbitals, whereas the fourth rule is for d and f electrons, right? See, the point 1 of the third rule says that each electron in the NS and NP group, if the electron belong there, will contribute 0.35 to the shielding constant. Each other electron, suppose you are considering the p electron of fluorine. So in fluorine we have NS2, 2s2 and 2p5, so that means there are 7 electrons. So if you consider 1 electron in p, that means there in the group there are 6 other, right? So we have to multiply 6 into 0.35. Similarly, anything which is n-1 shell contributes 0.85, and anything below it will contribute fully, that is 1. Okay. Now the only thing that changes from rule 3 to rule 4, that is for D and F electron, is that now anything which is not in the group left to it will contribute 1, right? This is because D and F electrons are shielded more strongly, right? And because D and F electrons are poor penetrating. That's why. Now let us take specific examples. Suppose we want to find out the Z effective, that is effective nuclear charge of the 2p electron of oxygen. Okay. Now first thing we have to write the electronic configuration. Oxygen has 8 electron, and we can easily write its electronic configuration as 1s2, 2s2 and 2p4. Now by applying the first rule we have to do the grouping, right? So we have these two groups there. Now just directly by applying rule number 1 of 3, right, we have what? There are 6 electrons in the outermost group, so there are 5 other electrons to consider. That means the contribution towards shielding will be 5 multiplied by 0.35. That will be 1.75. Okay. Now we have to consider the contribution of 1s electrons also. Now for oxygen 2p electron, the 1s electron are n-1 electrons. Therefore they will contribute 0.85 each. So the contribution from 1s electron will be 0.85 multiplied by 2, that is equal to 1.7. So the total shielding will be 1.75 plus 1.7, that is amount to 3.45. Therefore the total shielding, that is 3.45, should be subtracted from the actual atomic number, that is 8, to get the Z effective or effective nuclear charge, and in this case we have 4.55. Now you see this is only 57% of the actual positive charge that is in the nucleus, that is 8. In the next example, let us take a case where you can justify the electronic configuration of potassium by using Slater's rule. Now we know that for potassium we saw that the last electron, the 19th electron, goes to the 4s orbital rather than in 3d. Now let's see, by using Slater's rule, can we justify this? Right, for this what we have to show? We have to show that if an electron is in 4s, it is experiencing more nuclear charge than if it is in 3d. Then our purpose is served. Now let us first write down the electronic configuration on both cases, right? And we will do the grouping as usual. After this grouping, right, we consider each case separately. First, let us do the 4s electrons. For the 4s electrons, right, what we have, we do not have any other electron in the concerned shell, right? Now for the n minus case, that is 3 shells, right, we have 8 electrons, so it will be 8 multiplied by a 0.85 plus the all other things n minus 2 and below it will contribute 1, so there are 10 electrons. So overall our contribution, our the shielding constant will be 16.8, and our effective nuclear charge on the 4s electron will be 19 minus 16.8, that will amount to 2.2. Okay, now if we do the similar calculations for 3d, in this case what we will have, we still do not have any other electron in the same group, right? But now for we will have to apply the Slater's rule, fourth rule, and it says that anything other than the group, which is electron is not in the group, will contribute 1. So there are 18 such electrons, and they will contribute 1 each, so amounting to a shielding constant of 18 and giving a effective nuclear charge of 1. This clearly shows that the 4s electron is much strongly held by the nucleus. That means 4s electron experiences more nuclear charge, or in the other sense we can say that if the electron is in 4s electron rather than in 3d, the electron will experience more charge and consequently will be more stable. Now let us take a third and the last example of a transition element, say nickel. Now let us find the Z effective for a 4s electron and an 3d electron of nickel. As usual, let's write the electronic configuration of nickel, which has 28 electrons in our way, and then group it, right, by Slater's rule. Now see, first let us calculate it for the 4s electron. Okay, see, in this case there is one more electron in the same group, that's why it will contribute 1.1 multiplied by 0.35, right? And for the n minus 1 there are 8 plus 8, 16 electrons, so their contribution will be 16 multiplied by 0.85, and the rest 10 electrons will contribute 1 each. So this will amount to 23.95, right? And this gives us a Z effective for a 4s electron in nickel as calculated by Slater's rule is 28 minus 23.95, that is 4.05. Now if we do the similar calculations applying it to the 3d electron, right, what we have, in this case of course we will not consider the 4s electron, right? We have 7 other electrons which will contribute 0.35, and every other electron as the fourth rule of Slater states, that will contribute 1. That means we have 18 such electrons there. Okay, so 18 into 1. So this will amount to a total constant of 20.45, and we can calculate the Z effective for a D electron in nickel to be 28 minus 20.45, so that is 7.55. In other words, we can say that a D electron is more tightly held in nickel than a 4s electron, and this actually justifies why if we form nickel 2 plus, the electrons from 4s orbitals actually go away rather than from d orbitals. Okay.